Hello everyone, this is Ghanem Sabir with the Process Engineering Tips channel. Today we're going to talk about sizing a vertical process vessel. So process vessel is a pressure vessel within your chemical plant, not part of the storage tanks or the tank farm, would be a vessel within the process. And we will go over a case study and we will design the vessel in a way where you just put it on a specification sheet and you just give it to a vendor to get a quote on it. So please share and subscribe for more content like this. Thank you. The study we have is that size a vertical pressure vessel for 20% ammonia solution. So that's 20% ammonia and 80% water. The case study states the volume and state the operating pressure and temperature. And operating pressure and temperature is good to get some physical property, or also when you're trying to define the design pressure and temperature. And the volume, basically, or this is called the working volume, right? That's really important for the design as well. So let's put the info here. So this is 100 gallon, and this is 30 degrees Celsius, and this is, say, 30 pounds. Okay. Now, basically, at the end of this, you're going to get like a diameter and length. And that probably is going to be in feet, let's say. So maybe we should go ahead and just convert the gallon to feet. So just to make it easy, or gallon to cubic feet. And 100, I think that would be like 13.37 cubic feet. Okay, cubic feet. All right. Now, just follow these steps, okay, on how to size the vessel. So step number one, decide on the material of construction. And that's something you could either get by experience, or you could consult with somebody in the company that knows about materials in general, or you could consult even with the vendor, or you could find charts online, for certain materials and what material of construction are suitable for these chemicals. So something like ammonia solution, a carbon steel, would be something for it. You get carbon steel, the cheapest, but then you get stainless steel, you get different grades of stainless steel, and then you get even more expensive stuff, graphites and things like this, for more corrosive type of material. Okay. The next step is that you decide on the head type. Okay. And this is something, a trick, or not a trick, like just from experience, you could use this trick, which is, if your operating pressure is less than 100 pound, then you could just go with ASME flanged and dished head. Okay. And if your operating pressure is more than 100 pound, then you could go to ASME 2.1 ellipsoidal, which is basically a bigger head than this. This would be a little bit more expensive. Okay. So for something like our case, that would be basically you going with a ASME FND, which is like flanged and dished head. Okay. Now, next is decide the diameter. Okay, pick just a diameter. Now you could pick anything because this is an iterative process, and I'll show you how. So pick a diameter. Let's say 2 feet. Okay. So diameter is going to be 2 feet. Okay. Now, the next step is to calculate the volume head, and the volume head, you could use one of these two equations depending on the head that you have. So we have the flanged and dished head, which has this formula here, right? And that's basically the diameter. Sorry. And that would give you something around like 0.67 cubic foot. Okay. So that's step number 4. We've done with step number 4. Now, step number 5 is that calculate the nominal volume. So that's the nominal volume where you could calculate your length, or like tangent to tangent length. Okay. Now, so what this is basically your working volume minus your volume head. Okay. So in this case, our working volume, we said, is 13.367. Sorry. It's 13.367 minus 6 or 0.67, and that should give us somewhere around 12.7 cubic foot. Okay. Now, this nominal volume, okay, this will allow you to calculate your tangent to tangent length. So basically your vessel length, right? And you're going to notice here a 90%. This is actually a volume of a cylinder, cylindrical volume, right? So this is known, okay? It's pi over 4 multiplied with the diameter squared and then the length, right? But why did we add the 90%? Because you always want to keep a level of 90% in your vessel. So you need to go a little bit over than your working volume. In order to keep a cushion, in the vessel, and you don't want it to be full, right? And it's really depend. I mean, for process vessel, if it is something like hold a liquid, maybe you should go with 90%, 85%, if you want to even a little bit be more conservative. But if you have like a flash vessel where you're going to have like maybe gas and liquid, then in my experience, you probably should go with 50% liquid level target, okay? So basically what this equation, what it would tell us is that, okay, what is the length, right? So you could put the nominal volume, which is this number here, right? You know the diameter. And so then the only parameter that you don't know is length, right? So the length, actually, after putting this equation together, the length would come at 0.04 feet, right? So that you could say, okay, 4 feet and 2 inch or something like that, right? So something standard, right? And then after when you do that, then you need to do this sanity check, which is the length over diameter, because in theory, you want to be somewhere between 2 to 3, because that's a typical vessel would be that has a ratio between length and diameter 2 to 3. Otherwise, it's going to be a really weird looking vessel, right? If the diameter is big compared to the length, or if the length is big compared to the diameter, so it'd be almost like a pipe, right? So so that's why you want to be in the range of 2 to 3. I mean, for this one, if I put 2 over length over diameter, is going to give me somewhere around 2.23. So I'm good with that, But if you had a ratio that is lower than 2, then you got to go here and then reduce the diameter, make it like 1.5, and then repeat the case again. If it is more than 3, then you increase the diameter and then redo the same thing again. Okay. Now the next step would be deciding the design pressure for the vessel. So you could give it to the vendor, so they could quote you, the price for the vessel. And the design pressure really depend on what is this vessel is connected to. So if it is connected to a pump, you always go with the deadhead pressure of the pump, plus additional 10%, just to be in the safe side, right? So now, if this vessel is not connected to a pump, then you could go with something like, the maximum operating pressure with 10%. Say that there is, this vessel is connected to a pump with a deadhead pressure of 60 pounds. When we're saying deadhead pressure, is like whenever this pump is deadheaded, the max pressure it would give is 60 pounds, right? So in this case, you could say my design pressure would be 60 and 10% additional to it, okay? And then your design temperature, in theory, your design temperature should be the boiling point of your content at the pressure, at the operating pressure. Now, for ammonia solution, I mean, ammonia boils really fast, right? So it's going to be low, the boiling point. But assume it's, it's just water, right? And water has, 100 degrees Celsius boiling point. Depends on the pressure, of course, right? On the operating pressure, could be higher with a higher pressure. But you also need to add 10% as a cushion, okay? Now, unless if your material is really heavy and that number, the boiling point is going to be ridiculously high, then you could go with something like the max operating pressure plus 10%. But for this one, we could just say 110 Celsius, which is like the boiling point plus 10% to be in the safe side. If you like the video, please share and subscribe. And if you have any question, you could email me. I have my email in the bio. And hope to see you next time.